So we'll get 20 minutes worth of this. Now what I've done, this is the Year 11 booklet where I've summarised Newton's 3 laws, but we're going to use this booklet because it goes a little bit further in depth. We're going to look at Newton's first law, which is a little bit further down, but it refers to inertia. Now we need to speak about inertia. Inertia, before we look at inertia, we're going to look at mass. Mass is considered in chemistry, it's how many atoms something has, how much stuff an object is made up of. But a better definition in physics is how much resistance to change a body has. Okay? So you can literally determine how much mass an object has by applying a force to it and looking at how it responds to that force. Gentlemen, can you close the iPads, please? Okay? So we are going to be looking at acceleration. We've already covered acceleration, so we're good to now look at Newton's laws. Okay? Now, inertia, a better definition for mass is the inertial properties of matter, or how much inertia an object has. So we're going to look at an object's resistance to change. If something's 2 kilograms, it has twice the inertia. It is twice as resistant to change, and the change would not be as much. Okay? Please remember, mass is scalar, and we're using SI units, kilograms. I still have Year 11 students expressing answers in grams, which is terrible. You're out by a factor of 1,000. Now, here's what Newton said in Latin. An object at rest will stay at rest, and an object in straight line motion will remain in straight line motion unless acted upon by an unbalanced external force. Now, that unbalanced external force basically means that the sum of all forces acting on that object is not equal to 0. That's if it's unbalanced. Okay? The top part refers to it being balanced. Okay? Now we'll need Newton's second law to explain my next statement, but if the unbalanced force is not equal to 0, then we can say that the acceleration is not equal to 0. That means it's going to speed up, slow down, or change direction. Okay? But Newton's first law is more so the first bit. If things are not accelerating, then all of the forces acting must be balanced. Meaning, if the sum of all forces is 0, we can say that A equals 0. Okay? Now, Newton's first law is known as the law of inertia. Inertia is an object's resistance to change. Objects have a tendency to keep doing what they're doing. Now, if you are keeping doing what you are doing, then you are not accelerating. And there's a few different scenarios. I'm going to throw down some keywords because these are the words that prompt you to understand that an object is in equilibrium. Now, if we say that a car is cruising, that means that it's at a constant speed. Obviously, another important prompter is constant. Another one is at rest. Another is stationary. Okay? So what we're saying, if the sum of all forces is 0, then A equals 0. And there's obviously two different scenarios. You could have V equals 0, meaning that you are stationary or at rest, or constant. I'll just write constant. Okay? A lot of students have a misconception that if a car is travelling at 100 kilometres per hour, there must be this massive unbalanced force. No. If it's not accelerating, then all of the forces acting, weight, normal, forwards force, air resistance, they must sum to 0. Okay? So, think of an aeroplane travelling at 1,000 kilometres per hour from Perth to Sydney. If it's cruising at a constant altitude, it's in equilibrium. All of the forces that are acting on that object must sum to 0. If the plane wanted to speed up, slow down, or change direction, it would have to produce an unbalanced force. Increase the throttle, change your wing flaps, turn the engines off, have a wing fall off. all of those things are going to produce an unbalanced force and then an acceleration. Okay? Now, we've got some videos, and I think these are probably going to be copyright claimed if I try to upload this. So we might show you the videos at the end. Let's jump into Newton's second law, please. Now, Newton, 1670s, he was investigating the relationship between mass, acceleration, and force. Okay? So he was doing experiments, and we are going to do one of these experiments to sort of validate or confirm his findings. He said the following, and he said it in Latin. So here is the translation. The acceleration of an object will vary proportionate to the unbalanced force and inversely to its mass. Now, in that statement, there's two relationships. It's proportionate to the unbalanced force. That makes sense. The harder you throw something, the faster it accelerates. That makes sense. Inversely to the mass. The heavier something is, the harder it is to accelerate. That makes sense as well, I hope. Now, here's what he did. He did his experiments, and remember, we want to change one thing and measure the other. So let's look at, he changed the mass. So down here, could you put mass in kilograms? And then he measured the acceleration in meters per second. Of course, he kept the accelerating force constant. All other variables must be controlled. What he found was this kind of relationship. That is an inverse. This function is A proportional to 1 on m. And that was a very important relationship. Now, if we think it's an inverse, what we could do is we could plot 1 on m on the x-axis and A on the y-axis, and we should obtain linearized data. Okay? If we think that that is correct, then we could go y proportional to x. We could go, well, let's put 1 on m on our x-axis. And if it is, in fact, an inverse proportionality, we should get a perfectly straight line. There are other curvy things. There's 1 on x squared. A 1 on x squared could look like that. And a 1 on x cubed, and a 1 on x to the 4th. They all have that kind of curvy shape. Right? If it was 1 on x cubed, and we just did 1 on x, then you wouldn't get a linear equation. You would still get some weird wonky curve. So it's saying that it's not proportional to 1 on x. Now, we are going to be doing such an experiment. We are going to be varying the mass and measuring the acceleration. Okay? Then he did another experiment. He varied the unbalanced force. So down here, we're going to write force in newtons. And I'm going to find my black pen. And he then measured the acceleration up here in meters per second squared. His statement, which I just highlighted up the top there, is going to say it should vary proportionate. So what he found was a perfectly linear data. That is, A is proportional to F. So he combined these two proportionalities, that acceleration was proportional to that and inversely proportional to that. Now, normally what we do in science is we could say, well, let's combine these proportionalities. We would say A is proportional to F over M. And normally we would go A equals some constant times F over M. Generally, there needs to be a constant of proportionality that puts everything on this side, the units on this side, equal to the units on that side. But no one else had done that experiment yet. No one else had found this law. And in fact, there was no constant because the force was derived from the units of mass and acceleration. So he was the first bloke to investigate it. And literally the equation became F over M. Or we can write it in this triangle. I put this triangle here for students that struggle with rearranging. Or F equals ma. So this was Newton's second law. And again, I'm just going to add the unbalanced force, because remember, there could be two forces acting on an object and it could be in equilibrium. So we need an unbalanced force is going to produce an acceleration. And we can say that the acceleration is going to be the force divided by the mass. Oop, I need highlighter mode here. Now, as I said, before we turn the page, Newton, he was a very arrogant bloke, but he wasn't that pompous or obnoxious. He didn't say, you're going to name this unit after me. In fact, he was dealing with feet per second squared, because he was in England in the late 16th, 17th century, and mass was actually in pounds. So he didn't have kilograms and meters and seconds. It wasn't until the mid-1700s that the French went, we're going to use these units. So he would have had, I'm going to apply 500 pound-feet per second squareds on this object, and I will observe that it accelerate by 5 feet per second squared. Okay? Then, in the, I think it was 1720s or 1730s, the French went, let's make everything these units. He'd have to go back and convert everything. But now that we're dealing with metric stuff, the unit of the Newton is derived directly from the units of mass multiplied by the units of acceleration. So a Newton is actually a kilogram meter per second squared. Okay? And I think that weird bloke on Crash Course Chemistry sort of mentioned that that is a derived unit and that work is kilogram meter squared per second squared, and then power is kilogram meter squared per second cubed. These are weird units. It's hard to visual. So we're just going to say a Newton. Okay? We're not going to be applying 500 kilogram meter per second squareds. We're just going to say 500 newtons of force on an object. Okay? But again, dimensional analysis, if I put the units up here of force and divide it by meters per second squared, we get the units of mass. So dimensional analysis is going to work for us. Okay? Now, we are going to do this first experiment. We might even do it our very next lesson after our test. So you notice that over the page we've got a bit of a Newton's second law. What we are going to do is we're going to vary the mass, I think. No, we're not. What are we doing? No. Oh, hang on. Actually, F-M... Mass is constant. Mass is constant. We're gonna vary the. Okay, we're actually gonna do this one here. Okay. So it's not a very exciting experiment. You're expecting linear data. Hey, all right. But we can get some more information out of the graph, and we can compare experimental results with theoretical results. I will stop the recording here, gentlemen. Shh. But before I do, we have that acceleration is a vector, and so too is force. So could you just write down here, note, force is a vector. They have direction. So every single force that we are dealing with, we need to express its direction, up, down, left, north. Down is a good one. Weight pushes down. The table's exerting an upwards force. You have to write the direction. Okay? And we have to remember our rules for convention. If we're saying west is negative, east is positive. If you're doing an experiment and there's a force going that way, friction is going to be opposing. And so you need to explain that or describe that direction. Okay? So, we've looked at Newton's first two laws, but I'm going to show you some videos on inertia. So we'll stop the recording.